Welcome to our last module on this battery management system course. In this module, we will take a high-level look at the critical standards and practices that keep the battery safe, reliable, and also that keep them compliant with the global regulations. As you know, modern electric vehicles and energy storage systems are becoming incredibly powerful and compact. And while this is great for performance, it also means that we have to be extra careful about all of the potential hazards of these systems. In this model, we will explore the core functional safety principles of the battery management systems. We will learn about the different standardization bodies around the world, and also we will discuss some of the key testing methods that are used to verify the battery integrity. By the end, you will have a grasp of how safety considerations shape every step of the battery development and its usage, from the initial design to the end of its life. So let's start with it. Our agenda will be split into three main parts. First, we will talk about functional safety and the standards, why they are essential in the battery system, and how they will guide the development and the safe operation of the systems. Then we will cover the key testing methods that are used to ensure that the batteries that are coming out to the market are going to be safe. From the mechanical tests like vibration, crush test, to the thermal and electrical tests, we will explore all of them. And finally, we will wrap up with one of the most relevant regulations, that is the ISO 26262. This is a safety requirement that will give us the guidance on the development. So throughout these three topics, we will connect the dots within the theoretical safety concepts, practical testing, the regulatory framework, and at the end we will blend everything together alongside with the different topics that we have explored in our past modules. So let's start, and before we focus on the specific safety mechanisms, let's define what functional safety is, and let's examine why it is so crucial for the battery management system. So battery and functional safety is gonna be the discipline in the engineering that ensures that the system operates safely, as its name says, and it has to ensure that the systems will operate safely even when the parts fail or when we have unexpected conditions that might arise in any moment. In other words, functional safety, it's about designing and validating the system in such a way that in the presence of fault, the system either recovers gracefully or it shuts down in a very controlled manner. And in such a way, we are able to protect the people and protect the rest of the equipment. So why is so important functional safety in the battery management system? So first of all, is the hazard prevention. As we have discussed before, batteries are meant to be volatile, and if they are not maintained within the strict voltage and temperature and current limits, we may release rapidly a huge amount of energy, and this can be a hazard for the different applications. So a functional safe BMS identifies all of these risks in real time and will take actions, such as, for instance, preventing accidents and controlling the current, shutting down the battery in case any unexpected operation. The second one is related to the user and the operational safety. Whether in an electric vehicle or in an industrial energy storage system, a properly designed BMS has to minimize the risk of fire, explosion, chemical leaks, and at the end, it has to safeguard both the users and the personnel that is doing any maintenance or service in the battery. There are different standards. One of those that we will discuss later is the ISO 262, that is an automotive standard, But we have also industrial system standards and other type of functional safety measures for certifications. Meeting all of these standards is going to be very important for accessing global markets and for reassuring the customers and to guarantee that our products is trustworthy. And finally, by preventing catastrophic failures, we will avoid warranty claims, recalls, and brand damage. Over the product's lifetime, robust functional safety measures can significantly reduce maintenance and operational costs, and this is going to be very important for our business. So, in summary, incorporating functional safety in the BMS is more about just ticking the boxes on the regulatory checklist, but actually is a very proactive strategy that we have to take into consideration to ensure that no matter what goes wrong in our system, the battery will be able to respond in a way that keeps the people and keeps the equipment and keeps even the environment safe. This slide introduces the major organizations and regulatory framework that will shape the safety of standards globally. As you can see, each region has its own legal structures, but they often reference and harmonize between them within the international norms. We have here, for instance, in the European Union, we have the regulation from the UN Economic Commissions for Europe that have broad influence not only in the European Union but also in various countries and regions abroad the world. We also have different bodies, for instance, in South Africa, in Japan, in India, in China, and each one of these will set the rules for safety, for the emissions, and the performance criteria that the vehicle components, including the batteries, must meet. It's very important to understand how all of these requirements at the end will be overlapping and how when designing or selling the batteries into multiple markets, we can take advantage of those overlapping on all of these requirements for safety. While it might seem very complex, the truth is that at the end, the universal goal for all of these entities is to ensure the product safety and to protect the consumer worldwide. So with the small modifications in the testing, we can apply to different markets because at the end, they all share the same motivation and the shared goal of ensuring safety products. Following that, in this world map, we are visually highlighting different markets and how the regulatory systems will interrelate. We have in many cases that certain certifications or tests are fully recognized by other regions, making it easier to gain approvals across multiple markets. For instance, you can see in the dark blue the ECE homologations that they are not only accepted in the European Union, but also they are accepted fully recognized in other regions and in other jurisdictions. So in this case, if you obtain the approval in one region, you might be able to apply it directly to a completely different market. Then we have with the border highlighted with blue, the partial recognition of this norm. So in, for instance, places like Mexico, South America, United States, and some other regions in Africa and around the world, some tests and documentation might be still required to open this market locally, but in general, a large portion of the work that is done by the European Union and ECE homologation has been already done. There are some other regulations around the world, and each of those have their unique variations. From a manufacturer standpoint, it is crucial factor in this different to know from an early stage what are the difference between the regulation bodies, and this will avoid expensive recertifications on redesigns when you are not following them, depending on the market where you want to, when you want your product to be released. Then in these slides, we see a range of standards specific to the battery management systems and to the battery systems in general. Each of these different standards will be addressing specific aspects of safety and performance. For instance, in North America, we have the UL 2580 that focuses on the battery safety for electric vehicles and outlines the electrical and mechanical abuse tests that these batteries needs to fulfill. And also there is this second norm, the side that details the safety and abuse testing for rechargeable energy storage systems that are also used in many other applications. In the case of Europe, for instance, we have the ISO 26262 and the EEC 61508. Both of them addresses functional safety across the automotive sector, particularly the ISO. This applies for systems that are used in vehicles on public roads, and this one other is a little bit more broader industrial in broader industrial settings. Alongside with this, we have, for instance, the R100 that sets the safety standard for electric powertrains in the European Union, and some specific standards in China and in Japan or Korea also. In practice, the companies typically will pursue multiple certifications at the time to be able to cover different regions and as well to cover end-use applications. So meeting these requirements is not just about a legal compliance. These tests and these guidelines also ensure the product reliability and the consumer trust. So sticking to more than one, it's always well received. Now that we have established the importance of functional safety and the global regulatory landscape very fast, but at least we have an idea of how it is established, the idea now is to explore specific testing methods for the battery safety, from the mechanical to the thermal abuse to the electrical stress, to highlight some of these tests so we can know in advance what is the evaluation that the batteries have to be designed for, and how to push the battery's limits, and how to be sure that the battery will remain safe under those real-world conditions, and also under those extreme conditions that at the end brings the confidence to our systems. So in this table that we have over here, we are giving an overview of the different tests and also showing which standards mandate at cell level, module level, and so on, and what are the different testings that they have to pass. So here in the left we have the different standards. And then we have split into the mechanical, thermal, electrical, and other categories of the different tests that the battery is gonna has to pass. So on the first side we have the mechanical test. These include tests like, for instance, the vibration, the crush, nail penetrations, and so on. And the objective of this test is basically to simulate real-world shocks, impacts, and mechanical stress in our system, and guarantee that even in the presence of those, the battery remains safe. Then we have the thermal testing. Some of the tests that we include here are, for instance, temperature cycling or temperature shock. And the objective of this is to assess how the battery handles extreme heat or extreme cold and how it will remain safe even in those conditions. And over here we also have the electrical test. This includes, for instance, short circuit, internal or external short circuits, overcharge, over discharge. And all of these tests will say how the battery can cope with abnormal currents without catching fire or exploding or anything like this. As you can see in the table, each of these standards cover or have a different coverage of this test, and some require more rigorous evaluations than others. Basically, this will be reflecting the local priorities and the technology landscapes that each of these standards are trying to address too. So depending on that, we also have to define which of the standards is, and the testing procedure exactly for vibration is not going to be the same in all of these standards, but they will be slightly similar. In the next slides, we will present the description of some of these testing, so you can get an idea of the procedures and what are the pass and fail conditions of all of these testing methods that are required. And let's start then with a thermal method, that is the thermal cycling. The objective of this test, of the thermal cycling, is to put the battery through repeated heating and cooling cycles, going from very high temperatures to very low temperatures and having those strong changes in the temperature continuously. In this case, for instance, according to the UN 38.3, that is another of the norms for battery transportation specifically, we have a description of the procedure where the battery is going to be cycling between 75 degrees Celsius to minus 40 degrees Celsius. Switching between these temperatures often happens very quickly, and the idea here is to test the ability of the battery to handle that thermal shock. The battery must at the end retain at least 90% of the initial voltage or of the initial capacity, and only if after cycling the battery and having the post-test assessment we guarantee that the battery stays safety and has not lost much capacity, we can assume that the battery is safe. Practically, these tests will ensure that the electronics inside of the battery, like the BMS circuit for instance, will remain functional in climate ranges from the desert heat to Arctic cold, and it also confirms that the battery casing and the enclosure of the battery and the seal can handle the rapid temperature changes without cracking, leaking, or compromising the safety of the full battery pack. Another scenario here is the extreme heat scenario. In this case, the battery is going to be exposed to very high temperatures, up to 130 degrees, for instance. And this may be done in putting the battery inside of a climate chamber or by simulating scenarios where the battery heats itself through rapid charge and rapid discharge cycles. So this is another test that is going to be very important because the excessive heat is one of the most common reasons and triggers for thermal runaway, which at the end will lead to fires and explosions in our batteries. So with this test, we want to ensure that even in high temperature, extreme temperature conditions, the battery will stay safe. The idea and the assessment that we will have is to look for any leaks, for smoke, or for unusual chemical releases that might indicate failure in the battery in case of this extreme heat exposure. Realistically, EVs might face high temperatures environments. For instance, you can think when a battery is parked under the sun, and in those cases the temperature inside of the vehicle can increase a lot. So this test will ensure that the batteries remain safe and functional even under that severe thermal stress in all of the components and in the battery as well as in the BMS. Then we have an electrical test. In this case, this is a short circuit test. So the battery and the protocol says that the battery is going to be heated to a stable temperature. Often this is going to be around 55 degrees Celsius. And then it is going to be subjected to a short circuit with a very, very low external resistance, something less than 5 milliamps. And the goal here is to see how the battery reacts when there is a massive flow of current for a momentary and short time. In this case, the BMS has to protect the system to avoid, for instance, any increase in the temperature and potential failure, explosion, or fires. So the battery, in this case, the criteria for passing is that the battery must hold together without disassembly, without any rupture, without fire, both during the test, and also it has to remain safe up to 6 hours after the test. And this is going to be very important because external short circuits can happen in real time due to accidents, for instance crushing, due to damaged wiring or water ingress into the batteries. So the batteries passing this test will exhibit robust design that can prevent the catastrophic events of a short circuit condition, that is very, very important for the BMS to handle. Another interesting testing that is also electrical is the over discharge test. This happens when the battery is drawn well below its safe voltage limited, and it is going to be forced to discharge further by applying an external current to drive the voltage into very dangerous levels. It also has, for instance, the other version that is overcharge, where we are going to charge the battery to voltage further than the safe operating area of the battery. So according again to the UN 38.3, in this testing, the cell is going to be discharged continuously beyond the recommended capacity. The passing criteria is that after this test is performed, there should not be disassembly, there shouldn't be any fire, no dangerous temperature escalation during the test, and also even several days after the test. And also, in case of we are testing a battery system, the BMS has to protect and avoid the over discharge. Realistically, the over discharge might occur if the device is left on for long times, or in case the BMS fails to cut off the power in time. So this test will ensure that in those worst case scenarios, the battery won't fail catastrophically, but it will stay safe. Up to this point, we have covered the global safety standards and the most important battery test. We will have a very short introduction into the ISO 26262 and also into the ASIL ratings, that are the automotive safety integrity level ratings. This will help us to quantify the risk, the severity, the potential hazards in the automotive systems. And by understanding a little bit this framework, we will see how engineers pinpoint and mitigate the highest risk failure modes into the battery systems, specifically for that for those risks that can damage human lives. So it's gonna be a short introduction into it, but let's jump into it. So first, as it was mentioned, the ISO 26262 is the leading standard for functional safety in road vehicles. This standard will guide the manufacturers in identifying and mitigating potential system failures throughout the entire product life cycle. And the product life cycle means from the concept and the design of the product to the production and the commissioning of it after it has already served its life. Unlike other general safety standards, this is uniquely tailored for automotive applications, and it is addressing the complexity of the vehicles that are operating at the end in public roads. Why this standard matters so much for the BMS? So the standard will mandate a structured development process. This standard will tell you, in the case you are designing a BMS, that you must track safety goals and that you must track the risk from the initial concept phase right through the validation and into the production of it. Also, these standards will formalize how the teams collaborate, requiring clear documentations, cross-functional reviews of the different tasks in the development. It will ensure also robust testing frameworks, and at the end it will ensure that every design decision in the battery will remain aligned with the safety goals of the full vehicle. The automotive OEMs are increasingly insisting into incorporating the ISO 262 and adhering to these standards, not only preventing the legal financial repercussion, but also to position their BMS solutions for success in the competitive global markets. In general, these standards also give us a systematic or help us have a systematic identification of the hazards and the evaluation of their severity, the exposure, and how to control them, and ultimately determining how safe the system needs to be. I guess it's very important to understand this landscape and also how all of these guidelines set a foundation for building the BMS that can handle real road conditions and unexpected failures, and how the rigorous scrutiny on the automotive industry has to be considered from in the whole product life cycle. The ASIL rating is very important into the ISO 26262 because it will measure the necessary safety requirements based on the potential impact of the safety of the system failures. So the ASIL stands for Automotive Safety Integrity Level, and this is going to be ranging from A, that is the lowest, to D, that is the highest. Each level will reflect the degree of stringency applied to the design, the testing, and the validation. And this is going to be based on 3 key factors. The first one is going to be the severity. And this is the severity. We are going to be measuring it to determine how severe the consequences are if a failure occurs. For instance, losing battery power at high speeds can pose a critical hazard to the occupants of the vehicles and other road users. Then, besides of the severity, we have the exposure, and this means how often the vehicle will be in operational scenarios where the fall might lead to a hazard. So in an electrical vehicle, for instance, that is going to be used daily, Certain failure modes can have a high exposure ratings if they can be realistically occurring anytime the car is running. And finally, we also have the last of our key factors is going to be the controllability. And this says how easily the driver or the system can prevent the harm once a failure has initiated. A sudden battery shutdown at a freeway, it can be harder to control than an issue that develops slowly while the driver have a lot of time to react. All of these and the different AC levels of all of these BMS functions, for instance, will have important implications in the BMS. So first, it will reflect the complexity of the design. If we have features that are, for instance, ASIL-D, are requirements ASIL-D, for example, this will call exhaustive design reviews and also fault-tolerant measures and rigorous testing, and all of this to guarantee that is going to be that we will guarantee that it is extremely low likelihood of the danger of a dangerous failures to arrive. If the BMS is rated to ASIL-D, we expect to incorporate redundant sensors, to have a robust error handling software, several layers of hardware, safety mechanisms, and all of these will increase, of course, the price of the product and the complexity of the product. Also, this will have an implications in the documentation and the life cycle of the product. The higher the ASIL level is, it will demand more detailed documentations of hazard analysis and safety validations. Every design change must be traceable to safety requirements, forcing the teams to maintain strict revisions, control, and accountability on all of the features in the BMS. Also, the testing and the validation is going to be very related to the ASIL level. You will need more stringent test strategies like hardware in the loop simulation, stress test, thermal runaway, short circuit scenarios. All of this has to be tested every time that we implement a new version in our BMS if we carry high ASIL ratings. And another implication is on how the development teams collaborate in the execution of the different development tasks. So meeting high ASIL criteria is not just about engineering like some features and to including them into the system, and that's it. To put all of this into context also includes, for instance, the product managers, the quality assurance teams, and even the users. Everyone has to be aligned with the safety goals of this product. Ultimately, the ASIL ratings will shape nearly every step that we do in the BMS development. This will ensure that the safety critical features, like for instance the current monitor, the thermal management, the fault detections, everything is going to be designed to the highest possible standard that is going to be appropriated to their equivalent risk level. It is not the same to design a BMS for a bicycle, for an electric bike, than a BMS for electric vehicle or a BMS for a truck. Each one has different use cases and also have different safety goals that have to be aligned, and the ISO 2626 and ISO 262 will give us the framework for design based on it. With this, we conclude this course on battery management systems. Congratulations on making it to the end. Over the past module, we have covered everything from the BMS architectures, the core functionalities, the communication strategies, advanced safety features, and here in the last modules, the global standards that will shape the battery industry. A last message is that the future of BMS is very dynamic. Electric vehicles will continue to rise in popularity, energy storage systems will become more and more the integral element to the renewable energy solutions, and even wireless technologies will grow more sophisticated. All of this will keep us evolving in the standards, and the technology breakthroughs will be the key to staying at the forefront of this very rapidly advancing field. So thank you all for participating and for the attention throughout this course. We hope this insight equip you with the knowledge and the confidence to excel in the field of battery management systems.